So welcome to session 10. I guess this is classical thermodynamics. And our first speaker is going to be Elijah Thimsen, who I see is ready. And Elijah, whenever you want, just take it away.
Can you hear me?
Yes.
Perfect. Yes.
Okay, sorry. Okay, thank you all for coming. I'm going to continue the discussion on MAXIP entropy production because that's turned out to be a fairly useful thing to us. My group is interested in predicting chemical end states in non-equilibrium plasma chemistry. And we're interested in that for process design in the context of the electrification of the chemical industry to use renewable electricity. But I think some of the, we can certainly contribute to the discussion on sort of general principles that govern end states in non-equilibrium systems. I'm at Washington University in St. Louis in the Department of Chemical Engineering. Okay, so today is going to be focused on non-equilibrium thermodynamics. Non-equilibrium thermodynamics has two regimes, the linear and the nonlinear. Linear is close to equilibrium, and it's been well argued by Prigogine and others that the entropy generation should approach a minimum in the linear regime because you're close to the maximum. If you're talking about a chemical reaction, then the linear regime is described by the reaction affinity with respect to the thermal energy being much less than 1. So basically, you know, the potential of this reaction needs to be much less than the thermal energy. If the reaction affinity is on the order of the thermal energy or greater, then a chemical reaction operates in the nonlinear regime of non-equilibrium thermodynamics. And just to remind you, the reaction affinity is defined as the negative of the sum of the stoichiometric coefficients for different species participating in a chemical reaction multiplied by their chemical potentials. And this nonlinear regime is interesting because many systems that we don't really know how to describe with thermodynamics operate in this regime. Of course, the Earth is a notable example. So we don't really know how this works well yet. Dissipative structures have been proposed, but if you want to be quantitative, you can calculate the entropy production in this nonlinear regime as a sum of thermodynamic forces times the respective flows. And of course, the second law says that that is positive semi-definite. There are proposals, as we just heard Swenson talk about, as well as Kondapudi yesterday, that the entropy production in the nonlinear regime is hypothesized to be maximized at stationary end states. And I came into this idea through the work of Kleiden, but I'm aware that many others are working there as well. And so this is the hypothesis that we're going to explore today for non-equilibrium plasma processes. So this is a digital photograph of one of our experimental reactors. This is a radio frequency plasma reactor generated using RF power at a frequency of 13.56 megahertz. We flow gases through this partially ionized gas, and they react to form various species, and then they leave this environment and enter a recombination zone. And so this plasma is defined by a set of state variables. You get two additional ones. We can measure all of these things in our experimental reactor. You get two additional ones. One is the free electron density. So this plasma is a soup of free electrons, ions, and molecules. And so there's a free electron density. But what's really interesting about these systems from a thermodynamics perspective is that this electron temperature is extremely hot. It's about 100 times higher than the background gas temperature. So the background gas temperature is about 800 Kelvin. The electron temperature is about 70,000 kelvins. These electrons are very hot, and they coexist with the cold gas at the same macroscopic location in space. And so this is clearly a non-equilibrium system. And furthermore, it operates in the non-linear regime. And that's demonstrated by these experiments where we fed gas mixtures with different initial compositions, but the same volumetric density of argon, carbon, and oxygen, initially starting with CO2, which is the equilibrium state at this temperature and pressure, and alternatively starting with carbon monoxide and oxygen. And both of these different initial configurations approach the same stationary state for long times in the plasma, and that stationary state is very different from the local equilibrium state at this background temperature and pressure. And so you can calculate a reaction affinity for that stationary state, and it turns out to be about 50 times higher than the thermal energy based on the background gas. And so clearly this chemical reaction is operating in the nonlinear regime. Okay, so the research question we're hoping to answer is, how does the entropy production in a non-equilibrium plasma behave as the system changes from its initial to a stationary chemical state? And of course, the hypothesis is that the entropy production will attain a maximum value at the stationary chemical state. So the methodology is going to use experimental data to extract rate constants, and then build a model to calculate the entropy production rate as a function of time using those rate constants, and then answer our question of interest. So we conceive of this kinetic system as a 0D if you're an applied physicist, or plug flow reactor if you're a chemical engineer. And so basically we have plugs of flow going through a cylinder. We don't consider mixing with any adjacent plugs. And so effectively you can transform space into time using this very standard chemical engineering concept. And so the residence time in the plasma, again, there's two zones. There's a plasma zone, which approaches one stationary state, and then there's a recombination zone, which has a different end state. And so we control the residence time in the plasma. We can calculate that just by the volume of the plasma divided by the volumetric flow rate. And we can control the volumetric flow rate of the gas while keeping the composition constant. So that's treated as an independent variable. So we have control over the residence time in the plasma, and we can measure composition downstream after recombination has occurred. Okay, so the kinetic system is the simplest possible reaction system that can explain the results we see. There are two reactions. Both of them are elementary. One is the dissociation of carbon dioxide. The other is the dissociation of oxygen. What's different about these reactions in the plasma is the rate of the forward process. So the forward process is driven by impact with these extremely hot electrons. And so the forward process is driven at a much higher rate than it would be in a thermal environment that's governed by local equilibrium. And so that's the forward rates are what drive the process away from the value you would expect at the background temperature. So from the experiments, we'll get K1F, K1B, K2F, and K2B. Okay, so this is what a typical concentration transient looks like for this model. These transients are for two different initial conditions. One is CO2 in argon, the other is carbon monoxide and oxygen in argon initially. You can see that in the plasma, the CO2 is dissociated and it forms carbon monoxide and atomic oxygen. And then after these species leave the plasma, of course, that atomic oxygen is extremely unstable. And so it readily reacts with the carbon monoxide and associates to form dioxygen. And then what we observe is the gases after the recombination process has occurred. And you can see that this kinetic model works in the sense that the observed composition and the composition at the end of the plasma are independent of the initial condition. And so we can hit the stationary state in the plasma. So now what we do is we tune this model. And so in the model, we change the reaction time and look at the composition that's observed after recombination. And what we do is we tune those rate constants until the observed composition as a function of the prescribed residence time matches the experimental results. And I won't say that this tuning is perfect, and the reaction model is certainly oversimplified, but we get fairly good agreement between the solid lines, which are the model predictions, and these symbols, which are the experimentally observed points. And I'll just, the dashed lines, as a reminder, are the equilibrium compositions at the background temperature of 800 Kelvin. Okay, so now we need to calculate an entropy production. And so to do that, we need to define a thermodynamic system. And so we conceive of this system in the following way. There's a high temperature thermal reservoir and a low temperature thermal reservoir, and heat flows from the high temperature to the low temperature through the reaction system. The high temperature reservoir interacts only with those very hot electrons. And so the heat from the high temperature reservoir maintains those electrons at a constant temperature TE. Similarly, the low temperature reservoir interacts only with the gas molecules and maintains those gas molecules at a constant temperature Tm. And so the constraints are that the density in the reaction system is constant. As I said, the temperatures are constant. We make an assumption that the average specific heat of the gases inside the reaction system doesn't change with time. That's not strictly correct, but it's approximately true. And as a result of the temperature being constant, the density being constant, and the specific heat not changing, the internal energy of the reaction system is a constant. So then you can do an energy and an entropy balance and observe that the electron temperature is orders of magnitude higher than the gas temperature, and arrive at this expression for the entropy generation. So it has three terms in the bracket. The first term is the rate of reaction for reaction 1 multiplied by the affinity of reaction 1. The second term is the same thing for reaction 2. And then we have this term Q dot M, which is the heat that you're dumping to the cold reservoir. And of course, that bracket is multiplied by the inverse of the temperature of the cold reservoir. Okay, so we need to specify what that QM is. And so you need to think about how the heat is flowing through the system. And you could specify a large number of possible mechanisms. We chose to specify 3. Really only 2 of them are important. Really only one of them is important, and that's the vibrational mechanism, but I'll describe them all. Anyway, so the first mechanism is that we have heat flowing from the high temperature reservoir to the electrons, and then those electrons are colliding with gas molecules. For example, CO2 could be carbon monoxide or oxygen, to generate vibrationally excited states, and then those vibrationally excited states are quenched by gas molecules, thereby transferring energy to them, and then that heat is dumped to the cold reservoir to maintain the gas temperature at a constant value. Similarly, the chemical reaction produces heat. So we think the first step, the forward reaction is endothermic, and we think about that heat for the endothermic reaction being supplied by the electrons. And then the back reaction is exothermic, and that heat is dumped to the gas. And again, that gas dumps its heat in turn to the cold reservoir. Momentum transfer is a similar thing to vibrational excitation, only it's less important. So, okay, so we need to calculate these heat transfer rates in terms of things that our kinetic model is giving us, which are concentrations as a function of time. And so the heat dissipation via the back reaction is straightforward. The collisional processes have the same general form. It's the energy transferred per collision multiplied by the product of the density of the species participating in the collision, multiplied by a rate constant that involves an integral of the collision cross-section over the electron energy distribution function. And so you can see here for vibrational excitation, which is the more important heat transfer mechanism, the vibrational excitation cross-section for carbon monoxide is significantly higher than either CO2 or oxygen in the energy range of interest. The blue plot is a Maxwell distribution at an electron temperature of corresponding to 6.2 eV. So what we expect is, if maximum entropy dissipation is true, is that the system should favor configurations that have high concentrations of CO, because that will dissipate more heat from these very hot electrons. Okay, so entropy generation landscapes. So we can define the composition of this system by two independent variables. The first is the fraction of carbon that's present as CO2. And the second is the fraction of oxygen that is not bonded to carbon, which is present as oxygen. And so these landscapes are the entropy generation by each of these four components that I've discussed as a function of these independent composition variables. And so immediately what you can see is, as you would expect for a reaction that's moving away from the local equilibrium state, the entropy generation component due to reaction, the rate multiplied by the affinity, is very negative. It's very negative for basically any mixture you can imagine. And so what that means is these plasma chemical reactions, which we know occur in reality, we can experimentally observe that, must be compensated by some dissipation process in order to satisfy the second law. Both the heat from the back reaction and the dissipation from momentum transfer are insufficient to overcome this very negative entropy generation by the reaction. Only the vibrational dissipation is sufficiently positive to overcome that negative sigma. And so now what we can do is we can plot the entropy generation rate as the system traverses from its initial to its final state. And so what I'm going to show on the next slide is a map that is the sum of these four maps. And so this is a map like the previous slide, only it's the sum of the four components. I picked four arbitrary paths here, starting from different initial compositions. The initial state is along the top bar of the map, the top boundary of this graph. And as the reaction, as time proceeds, the system goes down, and all four of these paths reach the same stationary state. And if you plot the entropy generation along these paths, you can see that for all four of them, and for any path you can pick here, any initial condition you can pick, the final entropy generation rate is substantially higher than the initial rate at short times. And so this is consistent with the system reconfiguring itself into a state that generates more entropy than it did in its initial state. There's an interesting feature here with the gray curve, in that it passes through this maximum before it finally settles down at the stationary state. And I believe this is due to this idea of constraints. So it's possible for the system to occupy a configuration that produces more entropy than the stationary state, but that configuration is kinetically unstable. So it's an unstable state that doesn't sort of comply with the constraints. So that's perhaps a wrinkle in the idea, but clearly the final entropy generation is significantly larger than the initial for all initial configurations we've studied. Okay, conclusions. The first conclusion is that plasma chemical reactions are capable of moving away from the local chemical equilibrium state at the background temperature. That's unequivocal. The second conclusion, which is derived from the first, is that plasma chemical reactions must be coupled to a source of dissipation that compensates for the negative entropy production of the reaction itself. That's also unequivocal to satisfy the second law. The third is where it starts getting a little softer. So I would say that entropy production by chemically reactive low temperature plasmas appears to increase with time and attain a kinetically stable maximum at the stationary state. I think that our results are consistent with the idea that maximum entropy production principle applies to entropy generation by systems that are in the nonlinear regime. There's a typo there. The other thing I'll mention is that these low temperature plasmas are dissipative structures, in the sense that as soon as you remove that source of RF power, they disappear on a microsecond time scale. And so they only exist as long as they're dissipating work. Okay, acknowledgements. Najib Uner is a graduate student who has since graduated, who helped particularly with the initial stages of this work. He's on some of the early publications, and the financial support came from the National Science Foundation. So I'm happy to answer any questions.
Thank you, Elijah. So it looks like our second speaker is not here. So yes, whoever has any questions, please go ahead. Or Elijah, if there's something else you would like to say.
No, I think I said most of
Any questions?
what I came to say. Chat.
Any questions? You can write to the group chat if you have questions, or you can just say something. So I guess I have a question then, Elijah. Well, can you tell us a bit about the experimental apparatus? How do you make these low temperature plasmas for somebody?
Okay, sure. So can you still see the screen?
Yes.
Okay, so that's described in this publication here in the AICHE journal. So this is a vacuum system, so it operates at about 10 millibar. I don't have a schematic here, but so this is a fused silica tube, and we have mass flow controllers. So there's a vacuum pump downstream and a mass spectrometer that does the gas analysis. And we feed the gases into this tube using controlled flow rates by mass flow controllers, and we adjust those relative flow rates to keep the total amount of carbon and oxygen and argon in the system constant while changing the initial speciation. And then so you have the fraction of the different species, and you can change the total flow rate to control the residence time in the plasma. We measure these state variables. Of course, pressure is straightforward to measure using capacitance manometers. Temperature, background gas temperature is a little bit tricky. We use fluorescence decay temperature meters to do that because it's tricky to stick metal into these discharges. And we use a double Langmuir probe to get the plasma parameters, the electron density and the electron temperature. The plasma itself is generated using an RF power supply like you would find in the microelectronics processing industry. That applies a voltage of about 1,000 volts at a frequency, maybe not at these pressures, a few hundred volts at these pressures at a frequency of 13.56 megahertz. So you can't just hook up the power supply to the electrodes. You need to pass that through an impedance matching network that matches the impedance of the load to the impedance of the power supply to maximize the transmission efficiency. So there's the power transmission efficiency is about 70%. Yeah, gas detection is done by a quadrupole mass spectrometer. We calibrate that using known gas compositions with a three-dimensional grid of about 250 points. So I don't know if there's any more details of the experimental apparatus that I could describe, or if anyone has any specific questions, but I guess I could also be done if there are no questions.
Okay, thank you for that. It was a fascinating talk. So I guess we'll go ahead with our third speaker, Eduardo. I see that you're here.
Yes, I'm here.
Oh, I would like to wait until the actual time for Eduardo to speak in case people in the other session want to come to this session to hear him.
Okay, great, sounds great.